Hi guys, very welcome to this tutorial. In this tutorial we'll look at the flip Houdini fluid from a perspective of particles and volume. We will create something like this. We will emit fluid and we'll look at the initial state, how you can just fill objects with fluid. We'll look at some issues with volume preservation and also fixing this problem. And we will go through these parameters. I'll explain you which meaning they have for fluid simulation. Let's begin first with our steps. The first step will be the geometry preparation, when we just get some scanned asset. The second step will be a collision preparation. We will just convert this geometry to VDBs for volume collision. In third and fourth step, we will create a source. And step number 5, we'll look at the initial state with some custom noise. And then we will look at the container optimization, that we only simulate what we need to simulate. And in step 8, I will show you some custom visualization tools that we like to, how we can visualize very important attribute like speed or vorticity. Okay, great. Then let's begin with the first step. Geometry preparation. I just fly through the steps because it's not the topic of this tutorial. If you have any question, just ask me and I will be glad to answer them. As you see here, I have already loaded the file here. This is a scanned object that you can download from a link that I will put in the description below. I have a couple match sizes here and transform nodes to get this guy in the middle of the grid and with a proper scaling. You see it's about 4 meters now. Then I reduce the geometry and I cache it with a cache node. And you see, and now we have low resolution version for collision. Then what I did here, I used the delete SOAP to delete the top because we don't need anything for collision here on top. And then what I also did, because we will emit fluid from here, and I don't need this part for collision. What I did here, if you look here, I just cut this nose away and I have now only this collision geometry. I use couple extrusions here because as you see it's not waterproof geometry and there is very difficult to create VDB out of it. I created a couple extrusions here. By the end of the day, we have something like this with extrusion. And then I just do a VDB from the polygons here with voxel size of 0.01. And I just cache it to the disk. Okay, let's move on to the next one. Okay, let's create the source. I'll explain you how I did it and then we'll create it from scratch. First thing first, we need a geometry. I'm blasting this point for getting a position of my source. Then I use the attribute wrangle and I create p-scale attribute and this channel vex function. By pressing this button will create the p-scale slider, and I use here copy to point SOAP and copy new created sphere to this point. As you already know, if you change now the p-scale attribute, the size of this source will grow or shrink. Then I create a flip source node. What this guy does, if you look carefully, it creates volume and also the particles. From this time, we will look at this, as I already mentioned, as a mix of two things, particles and volume. If you look carefully here on the surface node, it has the volume part and it has the particle part. If you look inside your flip solver, it also have your particles tab and also your volume tab. And if you look here, also you get your surface volume and particles. You can also separate them with a split node using this expression. On this side, you will have the volume and on this side you will get the particles. If you look here inside the volume source, there are a couple expressions. Here, 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 or here. Let's see where they're all coming from. First, let's look at the voxel size. Voxel size is a result of the particle separation of fluid, a flip fluid object. Is a multiplication with the particle fluid object grid scale. If you go inside your .NET, you will find this flip fluid object. If you have over this particle separation, you will get this particle separation that we mentioned here, and also grid scale will be this guy here. Okay, let's see what this guy is doing. The particle separation is amount of particles within the fluid grid. For example, if you look at the particles here, if I increase this value, it will decrease amount of particles inside the voxel grid. Let's go back to here. What this guy is doing is the volume grid scale. If you look at this one here, if you change the resolution here, it will increase or decrease the resolution of your volume. As I already told you, the flip simulation is the sum of particles and volume. You will see it here because you see here you have this volume tab and also particle tab. Inside your flip solver, you also get this particle and volume tab. And also here, as you're already familiar with this is some parameters has a connection to particles, and some of them has connection to volumes. To be able to move a particle or fluid, we need some kind of velocity. First, I explain you on this simple example how to create the velocity for these points here that we already know or already saw. For this, I have 2 points. One point is on a grid, and the second one I just move a little bit to the other position here. And what I'm doing here, I'm calculating the velocity vector. And this velocity vector is a sum of the subtraction of the vector of this point and this one. What I'm actually doing here, I just grabbing the position of this vector coming inside the second input here with the point vex expression. I think just give me a vector of the first input. I like to have a position vector, and I like to have it from a point number 0 because we have only one point here coming inside. What I'm doing here, I just saying create a new vector, name it to velocity, and subtract this position vector from this one, and then by the end of the day just multiply it with another slider here. Now let's see the result. If you just activate this one here, you will see if you move this guy here, your direction of your velocity is updating. And also you have this second slider that you just can change the length or the magnitude of your vector. Okay, let's see how to implement it here inside our setup. What I did here, I use instead of point a sphere as a second point that I can change position of. Then we already have our source, and what I do here, I match position to my source sphere. What I do here, I extract centroid of this point because I need only one point. And I know what I did here. Okay, this is my aim position. This is transform node that I use here to change my point position here. And also I extract centroid of my original source geometry. And I did the same thing here. I just write it inside one line, but actually what it's doing is the same thing that you will look here. It is grabbing the position of this point here with this expression, and I just subtract from my current position this position, and I create velocity vector. There is no multiplication because I think I multiply it here with a noise. Yeah, you see here I multiply with this channel is my multiplier here. Okay, then what I do here, as you already know, we have here the surface and also points. What I do here, now I'm copying this velocity from one point on every point of this incoming geometry. With copy to point, you see I just take attribute velocity and I just copying from here to here. Now you'll get this. Then what I do here, I just take this one and I multiply it with some ramp here, because I like to have some noise here. I don't want to have everything the same. What I did here, I saying just take my current velocity and multiply it with a ramp based on my PT_num, because this you have here, I don't know how many points you have here. You have about 701 point. It will go through and create a value between 0 and 1. And then you have your channel ramp that you can just expand here. You see this, it will change your scale of your or magnitude of your velocity here. And what I do here also, I multiply it at the end with this slider here. If I like to have more velocity or less, I can change it here. Okay, let's create a source and velocity from scratch. What I do now, I will blast this point inside this geometry. I use a blast node. I set to points, delete non-selected. I connect it here, and I just select this one and press enter. Now you see we isolate this point. And now I like to have a sphere on a place of this point. I just go here, make a polygon sphere, frequency 220, use copy to point node, copy to points, and now we have the geometry. On a place of this point. But this is very big now. Now create a p-scale attribute to be able to resize this sphere. I use a wrangle. I rename it to size. And I just write f at p-scale. P-scale is already a global variable that's recognized by Houdini. And I just create a slider with channel f vex expression, vex function. I rename it to size, close parenthesis, semicolon. And if I press this button, you see now my sphere is disappeared. Now you see I can change the size of this sphere. Okay, I set it to 0.02. For this, I will use another sphere. I just copied this one here with holding Alt. I go back to 2, I think, because I don't need so much resolution here. And maybe I go here for Alt 3. And now I like to first match the position of these two spheres. I just go here and create match size. Okay. And now I like to move or transform this geometry as an aim for my velocity. I create a transform node. by default, the gizmo of this transform node is down here. I like to move it here to be able to move this sphere to the position, to my aim position, because I like to have some velocity in this direction. I like my fluid flows in this direction, not just falling down with gravity. I will use here on a pivot transform the centroid expression. And for the centroid, I will use the geometry. Just go outside of this and just take the copy to point 1 here. And we have to type d underscore x for x position. I just copy this guy and paste it for y position and also for the z position. Now you see your pivot point is now here. Now I like to just move my aim somewhere here. And now I like to just calculate the difference of these two vectors. But I have, in this case, the geometry. I like to have, instead of this geometry, only 1 point, and also instead of this geometry, also only 1 point. And this is very simple to do. I just use extract centroid. What this node does, if you just get rid of this name here, it will give you a point instead of your geometry, in the middle of your geometry. I just copy it also here. And now you see we have 1 point here and 1 point here. Now let's use our attribute wrangle to calculate our velocity vector. First, I like to grab a position of my aim. I would do vector aim, and I use point this expression to read the attribute p from a first input from ptnum 0. Because we have only 1 point, this will be the point number 0. Okay, now we have this aim, and now I like to calculate my velocity. I will say v at v is equal v at p, this is the current position, or the position of this point, minus aim. Okay, let's now just show our velocity vector. And you see we have to just reverse it. What you can do here, just reverse this, guys, or you just can say aim minus v at p minus v at p. Okay, now we have our velocity vector. And if you just move your aim, it will automatically update your velocity vector. Now is the time for creating a source. I will highly recommend it to use Houdini shelf tools, because the shelf tools will create the very important connections for you. And then we will look at these connections and you'll be able to create them from scratch. First thing to do is create a dot network, because I don't like the Houdini way, because it will create a dot network outside my geo container here. Be sure that your dot network is activated here. And now what you have to do, you have to go to your particle fluid and click on this button. It will ask you to select your object, but before you do this, this is very important. You have to first select your last node, or the node you like to emit fluid from. In this case, this will be this guy here. And then I click emit. Again, I select this guy here, go inside my viewport and press enter. You have to select it again and press enter again. And you see now the Houdini does the connection for you. Let's see what it does. It created the flip source, a null node, and also here outside 2 nodes that we don't need, this particle fluid and particle fluid interior. You can delete this interior, and if you want, you can just copy and paste this guy here, or this guy's here, inside here. Because this is the nodes for meshing and caching, and I will explain this nodes when we go to visualization of our result. I just click here to get rid of this render color here, and you can go out here and just delete this particle fluid too. And now we have everything inside our container here. Let's see which connection Houdini did for us. Okay, let's look at your flip source first. What this flip source does, if you look at the information, it creates particles and a surface. As I already told you, we have particles and also volume. But you see the number of particles is 0 because our particle separation is very, very big. That's why we don't get any particles inside. If you look at here, we have a connection. If you like to just change this particle separation, you have to go inside the flip fluid object and change the particle separation here. Let's see. What is it? You see in flip object, we have a particle separation. And if you now change your particle separation to 0.2 maybe, or a little less, you will see you will get some particles here. If you go up and look at here on information, you also have about 786 particles. The second thing what Houdini does is this voxel size. The voxel size is multiplication of the particle separation and grid scale. If you look here, as the multiplication of those two guys. This voxel size is very, very important because we will use it when we create our collision to match the resolution of a flip. And also the Houdini does here a couple other attributes here. If you see here, we have here the jitter seed is just expression. If you just click here and press W for wireframe, you will see the particles. And if you just scrap, you see this jitter just changing this value with the time expression. Then we also have this oversampling. If you click it here, you see this shows you the connection here and also shows you this connection. You can find them inside the flip solver. If you look carefully, it's flip solver oversampling width, and also here the flip object grid scale. And for this guys, you see there is no way, just click on them and just get the connection. What you can do here, you can click on this guy and go to expression and edit expression, and it will shows you the connection. If you see here is an if statement. It's saying if this attribute is 1, then gives me 1. If not, gives me this value. It's just like one line expression that Houdini uses here. Okay, this will be the thing that you have to just recognize, and just if you do it from scratch yourself, don't forget to put these connections, or as I did before, I just use this shelf tool with a little corrections. Let's now move forward and look how we can transfer our velocity to our points here, to particles, and also make some changes inside our dot network. If you look now on your setup, we have a particles, and if you play your simulation, nothing happens here. Because we have no forces, the first force will be the gravity force, and the second force, we already created the velocity. Let's first add the velocity to our points here and randomize the velocity of these points. You see we have a velocity here, but we don't have it here. What I like to do, I like to just copy velocity to these points here. For this I use a copy attribute or attribute copy, and it's asking you for geometry to copy attribute 2. It will be this here, and from you get this guys, and you have to specify your attribute here. In this case, we'd like to have not the color, we'd like to have velocity. And now you see we have a velocities from the copied from this one point on this all points. But the problem what we have, the velocity is the same for every point here. Now let's just randomize it. I will use a wrangle node here. I will first randomize the length of this velocity with the ramp. I will create the float value. It will be rand. And I will say channel ramp, or first let's create a random value. I just say float rand v is equal. I use rand vex expression, and I like to have here e at ptnum, and I multiply it with some seed value. Let's first create a slider. I will do integer seed equal channel e for integer. I will name it seed, close the parentheses, semicolon, and I multiply this ptnum with the seed. It will gives us the random value from 0 to 1, and now just remap this value with a ramp. I just say float. I will say here ramp v is equal channel ramp. This is a vex expression. First you have to give a name for this ramp. It will be, I don't know, v ramp, and it's based on our rand v. Okay, and now let's create also the slider for overall multiplier. I just do float, and I would say mult. It will be also channel slider. I will say multiplier, and I close the parenthesis now. And now let's just adjust our velocity. I would say the v at v, because we already have this incoming velocity, is multiply equal by our ramp v multiplied by the overall multiplier. Let's click here to get our sliders. You see we have a seed, and if you look now on your velocity, multiply is 0, that's why you don't have anything here. You see now you have your multiplier, and also you can now just change your distribution or your magnitude of your velocities here. Now you see they are randomized, and now we have a randomized velocity here. Now let's see what's going on inside our dot network. If you look here and you just click on this guy, you see now we have a velocity going in this direction and also randomized. Okay, great. Now let's just add the gravity. For this, I will use the gravity force and connect it here. Go back to my first frame, and you see our fluid is now just flowing down. Okay, let's see how we can adjust the size of our container, because we don't want to simulate anything we don't need. Okay, I like to specify a bounding box here and create the volume for my flip simulation. I use bound node for that. I connect it to geometry. And now you can specify the bounding or lower and upper padding here. Just let's see, I just go here. You can use also the side view, for example, or front view here. And I go down now with, oh, it's a little bit stronger maybe, something like this. I change this one from a top, something like that. And maybe we just change this right and left. Okay, now I just go back here. This is top. And here you see we have to change this padding too. Will be something like this. Okay. Now I go back to perspective view, and you see this is the region of my simulation. I will create a null object. I rename it to container container. And now let's go inside the top network, and under your flip solver, under your volume motion, you see the size of container is very, very big. I will use here the bbox expression to get the size of my created container. I have to jump twice to get to my container here. And now you have to specify the size. You see we have here the X size, the Y size, and the Z size. Okay, let's do this. I just say d underscore X size, close parenthesis, just copy this guy, put it here, change to Y, and now change to Z. Okay, now we have our container, but our center is not right. I like to have centroid. What we can do, actually you can just copy this guy here, because just put here, and instead of bbox I use centroid, and you have to change this d size to dx, because we already use this expression. I just copy and paste it for y, dy, and we use dz. Okay, now you see, if you work now, your fluid will only exist in this region. Okay, now you're kind of familiar with the flip setup. Let's create it from scratch. I will create a new dot network. I will rename it to flip sim. Okay, and now let's create a new flip source. Flip source, this guy is. Okay, now let's go inside and create flip object, flip solver, gravity force, volume source, and now just connect them. This goes here, this guy goes to sourcing, and we have now our connection. You see, by default you get this initial state. I'll come back to it later and explain how it works, but if you go now to your flip object, just go inside initial data and just delete this guy here because we don't need initial state. And now let's create all connections here. Okay, let's connect the flip source too. I just connect it here, and I do here switch node. And we just now take these two flip objects and we'll change them because we would like to have also the velocities on this also, on this flip. Okay, great. Let's see first here. I just change my input now, and let's look at the flip source here. And now we have to connect the first particle separation and also voxel size. And I'll also explain what this shell thickness does, because you see by default Houdini creates these attributes, but we don't have this here. Okay, let's go inside here and make some connections. As you already know, our voxel size is the multiplication of particle separation and the grid scale. Let's go inside here. Just copy this guy here, copy parameter, and paste relative references here. And go inside again, or you can use the double and just copy it from here. See, now we have flip sim, and I just copy this grid copy parameter, and I do multiply and paste relative references. Now you have the voxel size here. Now let's copy the particle separation again, copy parameter, and paste it here, paste relative references. I will use here add time, or you can use the old vex expression, or not vex, but old edge script expression, but this is doing the same thing. Now let's see what we have now here. We have some oversampling here and oversampling bandwidth here. Just look at this guys here, and you see it's showing you this flip solver oversampling. Let's go inside. We have our flip solver, and under the particle motion, you have here under receding this oversampling. Just copy this parameter and paste this here. But first you have to look at here, you have to activate it, because let's first connect this guy here. And if you look at here carefully, I just show you the expression, edit expression, and you see it's go here to do band and also this recede. Just copy this expression and you can paste it here in your flip source, and just go here and expression, edit expression, just paste it here. But you have to change, because our flip solver, now the name of our flip solver is flipsim. Just copy this guy and just put it here. And also here, flip solver. You have to be careful because the paths have to be the same. In my case, it's object geo1, because I'm inside geo1 folder. I have flipsim. I think I .net and flip solver. It's right. You have to put inside here and also here. Apply. Now you see you have this already, and now let's just copy this one here. We already know. You have to just copy this oversampling, copy parameter, and paste relative references. Just look again here, you see you have this guy here multiplied by grayscale, this bandwidth, oversampling bandwidth, this will be this one. You see if you hover over this attribute, it will show you this multiplied by our grid scale again. Let's do it. Just go here, just copy this parameter, copy, paste relative references, and would like to multiply it by this one. I just copy this one, and I say just multiply by this guy here, paste relative references. Now you see I have 2 here. And now let's look at this guy here. You see this add rest attribute, just go to expression, edit expression, and you see it's going under solver enable rest. Let's look, where is it here? You just go here to your flip solver and you have the rest, and here is add rest attribute. You see here enable rest. Just copy this guy, copy parameter, and the paste relative references, and you see as you activate this one, this has to be also connected. This do all, you just can do the same, because if you look here carefully, if you activate this guy, it's already activated here. What I do here, I just copy this parameter, and I paste it also here, paste relative references, and you see by default this is off. And if you look now here and here, you will get the same thing. Just click everywhere here, or maybe we can click here. You see 2, 1.5, and 1.4, because we have to change our particle separation to 0.002. You see you go now here and you change it to 0.002, 2. And now you see we have the same thing here and here. Let's look at the at this one here, at the shelf thickness. I just go here and just press W, and as you see here, if you activate your shelf thickness, it will gives you a kind of shell here. And by default, if you look at here, if you copy this parameter and put it here, it will gives you a particle within a shell. You see, it's like a shell is empty inside. This is your decision. If you want a more fluid, you have to deactivate this one. I will say, okay, I don't want to have this. Okay, great. Now we have this connection already done for flip solver. Now I just look, I just repeat it here because we already did it in with this bbox expression. I just jump over and come back to you in a minute. Okay, I like to show you the power of Python. If you can script with a Python, you can do the cool stuff with it. For example, you can use this script to set the container size. You have to select the flip solver, just go here and just grab your object, container, accept it, and you see now it will automatically set your all connections here. The same thing you can do also for the creating all the connections here, because I already wrote the script. It create whole setup with all connections, and for me it's very, very time consuming. Just go through these all attributes and connect them, but now you can handle this too. Now the next step is how to connect this volume. It's actually very, very simple. You have to go to your volume, and now you have to go to your subpath first. Just go here, and in our case you go to the object, to geo, and I think it was out surface. Just accept it, and you have to initialize it as a source flip. And now you see we have our flip, and now you see it also use the velocity and also gravity. If you just delete or just disable your gravity, it will use only the velocity. Okay, let's see how we can bring a collision inside a scene. I just go back to my first frame, and I already brought the geometry that I extruded. I did some extrusions here, And now I like to make the collision object out of it. We will use a collision source for that. And this collision source have two outputs, one geometry output and one VDB output. I will create two nodes. This one will be a geo. And I just duplicate this guy here. And I say VDB. For flip, you need a volume collision. That's why we're using this collision source. And you see on this side, you have something like this. It's very low resolution. You see you have a collision surface. What is actually doing this collision source is convert your geometry to VDBs. I just maybe show you a VDB from polygons. And instead of a surface, you have to use a collision. And actually you have your voxel size also here in your collision source in the volume tab. And actually what you have here is the same result. Okay, but let's stick with this one. And as you already know, we have a voxel size here. And you can use your voxel size of your flip object here. You see this, we have here the multiplication of these both. You can grab the voxel size from here. You see you have already your voxel size. You just copy this and just paste it inside here. Paste relative references. Now you see you have very good collision for your setup. And I highly recommend it to cache this guy here because it can become very intensive if you have some animation on your collision object. In this case, I just let it this way. And now I show you how to bring this collision inside our flip setup. We have to create a static object. Then we have to have a merge node. The first input have to go here, the second from gravity. And now we have to just grab our subpath. You have to grab your geometry. And for the collision, you have to go to collision tab. Here, use volume collisions. We have a volume here. And instead of ray intersect, we use volume sample and bring our proxy volume inside here. I just say here VDB, accept, and I highly recommend it. I recommend to show your collision geometry, your guide geometry, collision guide, because what you see here is actually the geometry. And this is not the collision. Before you do anything, please check your collision. Just deactivate your geometry and you show this guy. It will take a little bit time to calculate this collision. You see, now it's looking good in this case. Don't forget to disable it because it will just, your simulation time will just jump up. Just deactivate this one. And now let's simulate our setup. You see now we have some strange display here. We have to change the guide under flip object. Under guides, you see under particle, it uses the sprites. What I do here, I change it to particles. And now you see we have this. Display. Okay, guys, that's it for this tutorial. For this first part. In the second part, we'll look at the volume preservation. You see on the left, we're losing the volume. We'll look at the particle resolution. You see we have here different particle separations. We look at the volume grid size. We have here different volume grid sizes and different behavior of the fluid. We look through the time scale. Now we have to just look now. And last but not least, we go over the custom noises, how to use them on the initial geometry. Because as you see here at the beginning, the initial geometry is just without the noise. Okay, great. Thank you very much for watching. If you like this tutorial, subscribe my channel, stay with us, and I'll see you in the next one. Bye.